morning. Welcome to the physics video lecture once again. It is Physics 105A, video lecture 35. Today we have a great topic. We're talking about nearly circular orbits, and we'll really see the power of the effective potential formalism. So, nearly circular orbits. And these are very common, and what we're going to talk about will also pertain to artificial satellites. We started talking about the Earth and the planets, about the Sun, and we saw Earth's orbit was not very eccentric at all. So naturally nearly circular. So we want to look at that closer, and definitely under the aspect of our artificial, say, Earth orbiting satellites as well. Yes, so we will begin with, we'll just write down what we have. So our energy expression, in which we've already replaced the angular velocity, right? So L squared over 2mr squared plus u of r is equal to E, right? That is our energy. We call this the effective potential, because we effectively have a 1 degree of freedom problem. And we can see, for example, if we had a circular orbit, then r dot would be 0. Okay. And we could just analyze the effective potential as we did last time. Also, we have the angular momentum L. So these are the two conserved quantities. The energy is conserved, angular momentum is conserved. I'll go ahead and write that. Energy conserved. And then L m r squared v dot. And here we can also write angular momentum conserved. Those were our two conserved quantities. Now for a circular orbit that we talked about last time, we of course have r dot is equal to 0, and r0, we have of course had that from the Kepler problem, L squared over m alpha. But also, for a circular orbit, we have phi dot is equal to a constant, is equal to, we define it as omega sub phi, right? And if phi dot is a constant, then you have L is constant, phi dot is constant, or is R0 equals constant. The whole thing is there constant then. So that's the situation for the circular orbits. Let me consult something before I continue on. Yeah, good enough. Okay, so what about the nearly circular orbits? This deserves a box of its own. So for the nearly circular orbits, r is no longer a constant, but phi dot we're going to retain as a constant, because corrections to phi dot would be second order small. So we're going to look at the effective potential again, which we've analyzed a few times now. So we have U effective of R, which is L squared 2mr squared plus U of R. We'll draw our generic Kepler problem effective potential just to have one here. And of course, that's the first one we want to look at. Yeah, here's our circular orbit. This is the picture I ended with in the last lecture. Circular orbit, E sub 0. Now what we want to do is change the energy to E sub 0 plus delta E. So we want to change the energy, but not change the angular momentum. So we have to discuss how that's possible. And what we're going to have then is R min and R max. If your delta E is small enough, you're close enough to E0, and your interval, you know, these will be actually very small quantities. The delta R will be very small, and it'll be symmetric. Okay, we'll get to that later. Okay, so how to change E from E0 to E0 plus delta E without changing the angular momentum, and not change L, question mark. So how do we do that? Well, imagine we have a circular orbit. So given a circular orbit, and here's our center of orbit, and there's R. If we want to change the energy, we have to somehow impose a force that is a central force, because a central force preserves the angular momentum, right? This is a central force problem. You have conservation of angular momentum. So you can imagine if you are a satellite spaceship of some sort and you want to change the energy but not the angular momentum, you just have to fire thrusters towards or away from the center of the orbit. That will change the energy. You've added energy. Okay. We'll do the rocket equation next semester, by the way, but it's clear you've added energy to the orbit and you have not changed the angular momentum. So the answer is, given the circular orbit here, apply a central force, right? Thrust, which is towards or away from the center of the orbit. That'll leave the angular momentum unchanged, but it will change the energy, and this circular orbit will now turn into an elliptical orbit if it's a Kepler problem. If it's not the Kepler problem, if it's just some general potential of the circular orbit, we're going to see what it does. Okay. Central force. So yeah, that's the idea. Now, okay, so we're now going to look at the relation between the change of the energy and the change of the orbit. Okay, so I'll put this here. This changes the orbit. The way it changes it, like I said, it puts you this higher energy with the same angular momentum, and so your orbit is now between, let's go ahead and write R min and R max. And remember, this was an effective one-dimensional problem. So we're in an effective, or we're in a potential well. And if we're in a potential well near the local minimum, what do we get? We get oscillations. So it changes the orbit. So we get, I'll go ahead and send this up. What we get next is oscillations in R. Remember, this is a differential equation. We know how to solve it. We know what the potential energy looks like, so we're going to get oscillations about R sub 0. Let's see here. Let's go ahead and keep this up. So the result of applying that central force, which is a thrust, the result of this orbital change is that now the radius r oscillates about r sub 0, the circular orbit. So in the same time that you have this circular orbit, you now have an r min and an r max, okay? And if you start here at r min, you're going to oscillate out to r max, back into r min, and so forth. It doesn't have to be a closed orbit. R oscillates about r0, and just from what we have here, conserved energy, effective potential, half mr dot squared, we can immediately write r of t is going to be r0 plus some small constant. I'll just call it a. I could actually call it delta r. Doesn't matter. Delta r cosine omega t, and let's ignore any phase in there. Okay, we'll just cosine omega t. Keep it simple. That's what we have because we're looking at a local minimum. We're saying, okay, what do? Second derivative criterion. So this frequency here, I'm going to call it omega sub r, with omega sub r is equal to the square root of u effective double prime r0 divided by m. Just our one-dimensional oscillations criterion. Okay. Nothing different than that. Okay. Okay, good. Also, we have that m r squared phi dot equals L, which had us saying omega sub phi was L over m r naught squared. And the thing is, we're going to keep this stays constant because its change, right? Principally, there's a small change in omega sub phi, but it would be small. It would be first order small in this delta r here. Okay, whereas omega sub r is 0th order. So we retain this as being constant, and so now what we have is, imagine this counterclockwise motion. That would have been your circular orbit, except the orbital radius is changing at the same time. You can try drawing it. Okay, gotta have a good wrist to draw that. So what we want to do, the first thing we want to do is apply this now to the Kepler problem, to the Newton potential. And I'll assign this as a homework problem. I'll go ahead over here now. So for the Kepler problem, for the Newton potential, we already know that these orbits are going to be closed. So they're not going to look like, okay, I'll try to draw this. If the orbits weren't closed, then you would sweep out all the area in that ring here. But we know for certain that the perturbations of the Kepler orbits will be closed because we know that they're ellipses. They're closed from the beginning. Okay. So that's what we're going to prove. So homework everything up there that we need? Yes. For u of r is equal to minus alpha r, show that omega sub r, which I just gave its definition here, u effective second derivative of r0 over m, omega r, okay, show that for, okay, let's formulate it this way. I already have the definition up here. In fact, I have both. I have omega sub r and omega sub phi, so just show that omega r equals omega phi. Omega sub phi. That's very important. And it won't be hard to do. You have to take your effective potential, put in your minus alpha over r. I'll just kind of get you started on it. First, u effective prime of r0 is equal to 0. That gives you your r0 criterion. And then the second thing, calculate u effective second derivative of r0. Construct this quantity, and make sure they're the same. Okay, and they will be. Let's consult the clock here. Okay, perfect. Etc. Okay, so once you've verified that, and it has to be the case, like I said, these are the perturbations of a circular orbit, just puts you into a Kepler ellipse, closed orbit, no problem. So once we've shown that, we want to do it for the general case, and that is very important. Let me explain the importance of that. This is the Newtonian gravity potential for a perfect sphere, for a spherically symmetric mass distribution. We will show that rigorously next semester. Right now we're just treating them as point masses, but it's true for a spherically symmetric mass distribution. Now, our planet, for example, our sun, the celestial bodies are not perfect spheres. For example, if they're rotating, they turn out to be slightly oblate spheroids, okay? Larger around the equator than they are around the poles. Slightly bulging out, okay? And what that does is it adds corrections to the Newton potential. So if the Newton potential is minus alpha over r, then the Newton potential for, if the perfect one is this, then for a slightly non-spherical object, slightly ellipsoidal, you're going to add some correction terms here. You're going to add a beta over r cubed, which we'll prove next semester. And what that's going to do is it's going to change the shape of this ever so slightly, and it's going to change the shape of the ellipse from a perfect ellipse to an ellipse that no longer closes perfectly, and that can then be determined astronomically whether or not that's the case, or to which degree that's the case. Okay. And that has to then be measured to actually ascertain if Newtonian gravity is really absolutely true, or if there are slight deviations from it. And what's amazing is we can actually access those problems just with our analysis of the effective potential. Good, so having said that, let us construct what we're going to do here. Okay. I'll rewrite what I have here. So we're doing the nearly circular orbits now. I'll just do a smaller version of these pictures, see what we can fit on this board. So just to have this up here, we still have our generic effective potential plus U of R. Okay, you guys dealt with it for the pure Newton potential. Okay. And we're looking at a nearly circular orbit, so we are at an energy slightly above this minimal one. Okay. So that we have a slight range of motion as described up there. And I'm now going to define what's called the apsidal angle. I'll do that right here. Apsidal angle. And basically, okay, let's write that we have an R min and an R max here, about a nearly circular orbit. Of course, we exaggerate these things. So there's the circle of radius R min, circle of radius R max, even though it's supposed to be very close together. So here's what we do. There's R min. Okay. It's the minimal. And here is R max. And we define this angle that's swept out here. This is the angle C. This is our apsidal angle. And what's happening here in terms of the trajectory, we're imagining we start at R min and then sweep out to R max. Is that dark enough? There we go. So that's how much angle gets swept out as we, oscillate between R min and R max here in this graph. So having swept out C like this, then as the orbit continues, it would sweep that same amount out again, and we'd end up somewhere down there. Okay. I'll just indicate that with the dotted line, just so you see we're not returning to the original point. So that's like pi minus a bit. We're going to end up something like down here. Okay. And that would mean we'd end up like that. And on and on. Okay. So there's our apsidal angle C. And that is defined as omega sub phi over a half period times T sub R divided by 2. That should make sense, right? Imagine the counterclockwise hand sweeping out time, and then there's a bead on it moving in and out. At this point, the bead is moving out, half period, another half period goes in. So for our Kepler problem, which of course, the perfect ellipse, then this angle would be equal to pi. Okay. I'll put that as a note. Well, we'll put that later. We'll find that later. Okay, there's another way to look at this though. And that is, we can also use omega sub r, T sub r is equal to 2 pi. Right? Omega t is 2 pi, so for the radius oscillation, that's the case. And we'll make a substitution. We got omega sub phi, T sub r is 2 pi over omega sub r. And then of course we have that 1/2. So that cancels. This is a more useful version. Well, they're both useful. This is the one we need. So it's pi times omega sub phi over omega sub r. And in fact, the way we're going to use it, pi divided by omega sub r over omega sub phi, like that. That's of course not yet. So this is the absolute angle. When it's equal to pi, we're talking about a perfect Newton potential. We do a little, if we add an approximation term or an expansion term, like I said, beta over r cubed, we're already no longer going to get pi, and then we have something to compare with astronomically. So what we want to do is get a once and for all calculation of this expression here. Once and for all. And let's see if we can pull that off. So we have the U effective up there. Let's see what we remember about this. Omega sub r is the root of U effective double prime of R0 divided by M. And then we had mr squared omega sub phi was equal to L, so we also had an expression for omega sub phi. Now we also had another expression there, or m v squared over r is equal to u prime of r naught, as you guys remember from the circular orbit discussion, and right, uniform circular orbits, we know about that. And this can be written as m r naught omega sub phi squared over r naught equals m, cancel one of those, r naught omega sub phi squared equals u prime of r0. So we'll make use of these. This relation here and this relation here in order to calculate this thing right here. So let's have a go at it. So we'll rewrite our effective potential and then take a couple derivatives. U effective L squared over 2m r squared plus u of r. U effective prime is equal to minus L squared over m r cubed plus u prime of r. And so we can see what r sub 0 is. It's first derivative criterion. U effective prime vanishes. So we have L squared over m r0 cubed is equal to u prime of r0. So that's one relation we have. Good. Now let's take the second derivative. U effective double prime. And we want to evaluate it at r0. First we take the derivative, we end up with 3L squared over mr to the 4th plus u double prime of r and since we want to evaluate it at r0, put an r0 here and here, and now we can get rid of this L squared over m r0 cubed, because that's going to be equal to 3 L squared over m r naught cubed is u prime of r naught, so 3 u prime of r naught divided by r naught plus u double prime of r naught. So now we're ready to deal with this. Let's see if that works. We have now C is equal to, this is our equations, R here, pi divided by omega sub r over omega sub phi. Omega sub r is the root of u effective double prime of r0 divided by m. And then since we're dividing by omega sub phi, we could put omega sub phi squared in here and keep going. That would be pi divided by, make some room here, u effective double prime, so we would have 3 u prime of r0 r0 plus u double prime of r0 divided by m. And then omega phi squared. But actually, we've got the divided by m omega phi squared, but the m omega phi squared is u prime of r naught divided by r naught. So u prime of r0 divided by r0. So once we simplify this is really beautiful. You'll notice we've eliminated all mention of L and anything like that, and in fact we've reduced it to an expression. We'll simplify it here, but it only involves the original potential and its derivatives, u prime and u double prime. So let's just simplify this and see what happens. So what we've obtained for our absolute angle is pi divided by, it's an r0 hidden there from sight. So 3 u prime over r0 divided by u prime over r0, that's just a 3. So 3, and then we've got a u double prime divided by a u prime, denominator brings that up here. So 3 plus u double prime of r0 times r0 divided by u prime of r0. So once and for all, we get the absolute angle for all central force problems with the potentials u of r. You can even see if you don't have the potential energy, if you have the force, you can express it in terms of the force as well, because u prime is force, u double prime is force prime, okay? Extra minus sign in there will cancel. So you can do this also in terms of force. I'll leave that, put that in your notes if you want. But now what we want to do is give this a try here, evaluate this thing and see what happens. We consult the clock. Perfect. So our examples now, and again, you see what this thing is that we just figured out. It's the amount of angle swept out between R min and R max. So that's for half a period of the oscillation of the radial position. At the same time, we're just having the angle sweeping out at a uniform rate. Okay, I'm going to go ahead and erase this. and we'll do a couple of examples. So, since there are two that we've specifically looked at, u of r is equal to minus alpha over r. U prime of r equals alpha over r squared. And u double prime of r is equal to minus 2 alpha over r cubed. So immediately we have u double prime of r0 times r0. That's going to be minus 2 alpha over r0 squared. Multiply one of those out. Divided by alpha over r0 squared, and we're just left with minus 2. And c is equal to pi divided by square root of 3 minus 2 equals pi. So there we go, closed orbit. Let's do another one of these. You can also see if u of r now has that extra term, right, that little correction term, beta over r cubed, there's no way you're going to get that 3 minus 2 and get a pi count. It's going to be pi plus something small. So let's look at the other central force that we talked about quite early was the half k r squared, the one that also gave elliptical orbits. Now this one's going to be interesting. So my next example u of r is equal to 1/2 k r squared. Remember we had these ellipses, and I had told you guys they're not Kepler ellipses, but they were ellipses for this problem. But yeah, let's calculate u prime of r is equal to k times r, u double prime of r is equal to k, and so, well, we can just do this. C is equal to pi divided by 3 plus what? U double prime of r times r, which is k times r divided by k times r is just a 1. Okay, so we just get 1. Pi over root 4, so that's pi divided by 2. So you might be wondering what's going on here. Let's draw our picture. So we've got an r min and an r max. And we had already learned that these were ellipses, so we're kind of curious as to what's going on. What's going on is that we sweep out from r min to r max in pi over 2. And then from r max back to r min, pi over 2, and all the way around. R min to r max, pi over 2, and so we get an ellipse. Okay, not such a beautiful ellipse, but we know it's an ellipse. And it is a closed orbit. Now, an analysis of this object here shows that you don't get many closed orbits beyond, primarily you get these two. Okay, you get these two, and other closed orbits will close after many, many circuits around here. So in a sense, they're not closed orbits in the same sense. Okay, let's consult the clock. This is a good place to leave it. there's a good homework problem I could assign for this apsidal angle. You know, I'll put it up here as a homework, and I'll probably get started on it next time, next lecture. But here's our project. Homework. Suppose U of R is equal to minus alpha over R plus beta over R cubed. We'll learn next semester that that's the next power in a series, okay? In terms of inverse powers of R, the R cubed. But this is one that becomes algebraically difficult to do exactly, so we have to do some kind of clever approximation. So beta is small. Well, what small with respect to what? Small in the sense that if we take the limit beta goes to 0, we're back to our result right here. Okay. So what we can do is treat it as a very small parameter and make little expansions. Okay. Calculate C. Okay. Now the thing is, you're going to have to do approximations to make it work, so it's going to be very interesting. You know, you're going to end up with this 3 minus 2 plus something small, and then so I'll just put your note. When you have 1 over the square root of 1 plus x, right? That is 1 plus x to the minus 1/2. Then for small x, what is that approximately equal to? 1 minus 1/2 x. For small x. So your task is to go into here, you know, just calculate this thing out as though you knew what it is. You've just added the beta over R cubed to your effective, do I have it up there? Do I have to your expression. Actually, you don't even have to use the effective potential. You're going directly off of these expressions here. And then under the assumption that beta is small, you can end up with a 1 over 1 plus something that you declare to be small, and that vanishes when beta goes to 0. And then you can make that approximation, and so you're going to end up with pi plus pi times something small, okay, that vanishes when beta goes to 0. So good, we'll look at this together some more, but this is a really significant result, actually, because satellites and planets and everything that are orbiting bodies that are not perfect spheres will have this effect. Okay. We're going to leave it at that and see you guys next time.